Okay, let's start this. Um, so my presentation is on the Ley Oxidation. I think it's really cool. I learned a little about it from some articles and some journal entries in on the American Chemical Society database. So let's begin. So the main component is a ruthenium salt, but they mentioned in one of the articles that ruthenium and osmium have like a large oxidation range. So they can be from like, I forget, like 2+ to 8+, which was really interesting. And when they complex with oxygen, they essentially are really good at helping form like oxygen carbon bonds. Osmium is a milder oxidant than ruthenium, so it's not really used. Ruthenium perruthenate, which is the RuO4, can be dissolved in organic solvents as part of a salt, either TPAP, which is tetrapropylammonium perruthenate, or TPAP, which is tetrabutyl ammonium perruthenate, and in the Ley oxidation you used TPAP. So TPAP, tetrapropyl ammonium perruthenate, it is a dark green solid. It is stable in air, which is really nice. It can be stored for a very long time, which has been very good. It is a mild oxidant and it's pretty selective. It won't react with a lot of stuff. They were talking about things like it won't react with like esters, epoxides, even a lot of protecting groups such as an acetal. And it reacts with primary and secondary alcohols to give aldehydes or ketones. And since TPAP is an organic salt, it can be dissolved in organic solvents, mostly acetonitrile and methylene chloride. And it has a co-oxidant and methylmorpholine and oxide, NMO. And the combination of the NMO and TPAP is the Ley oxidation. How is TPAP made? Well, you can either buy it. It's a little more expensive that way, but you essentially take ruthenium chloride, convert it to perruthenate by dissolving it in sodium periodate, and then put it in a solution of tetraammonium hydroxide, and then wash it, and then rotovap it, and then you would get TPAP. So this is the reaction of the Ley oxidation. So you have the TPAP, the co-oxidant NMO, the solvents, which are methylene chloride and acetonitrile, and then 4 angstrom molecular sieves. I defined it on the handout because I didn't know what a molecular sieve, and it's essentially a 3D crystalline complex of silica and alumina, so they're adsorbents, and when they're dry they let only certain size molecules through, in this case 4 angstrom. So I learned that from Sigma Aldrich. What you need TPAP, which is the catalyst, NMO, 4 angstrom sieves, solvents, and this can be done at room temperature or cooled if it's larger scale or like multi-gram scale. And the reaction is vigorous, so TPAP needs to be added slowly in portions, which is very important. So why is it so useful? It takes primary and secondary alcohols and it converts them to ketones or aldehydes. It's pretty selective, so that it works well with like multifunctional molecules. It can be done with room temperatured or cooled. It can be done at a large scale or small scale. It has pretty good yields and it's really easy to work up. So it's pretty easy to purify once you have reacted it. A big limitation is ruthenium is very expensive. Like the ruthenium chloride, 1 gram costs $48, and the TPAP itself, a quarter of a gram costs $54. TPAP breaks down at 150 degrees, so you can't really heat it too much. And depending on the molecule, there could be bad yields because the ruthenium turnover, the catalyst turnover doesn't like work so well. So I would maybe check the literature before you do like a specific reaction. Oxidation is vigorous, so it may need to be cooled. And if the reagent is too unstable, it can also give poor yields. But a good thing about the Ley oxidation is it works good with some unstable reagents, but other times it's not so good if they're too unstable. So some examples, this is part of a synthesis of prostaglandins. So they're naturally occurring molecules which some people wanted to synthesize because of their anti-cancer properties. I think in this step, the OTBS is being replaced with an alcohol, and I think that's being done by the TPAP. The next one is a reaction to synthesize an immunosuppressant minus priotin, and this is needed for people for things like people with transplants and whatnot. And as you can see, the primary alcohol is being transformed into an aldehyde, and that's one of the steps on the way to making the priotin. I found this article on the ACS website, but they had a mention of it in one of the references Professor Cermak gave me. I have references at the end. And finally, this is E-tributyl stanyl alpha beta unsaturated ketones. And so this is like a regio or stereoselective step followed by a Ley oxidation. And to get probably a good yield, the yield is like 85%, and it can be done at room temp, so that's very helpful. I forgot to mention, after this reaction was done, there was an aldol reaction. So, and then I think that's it. These are my references. So